this lecture we are going to discuss how to solve nonlinear problems using the finite element method. So, now nonlinearities in physical problems can arise due to many reasons. For example, you may have material nonlinearity, as in the case of plastic deformation of materials, materials with damage in them, materials with cracks, growing cracks, and so on. So, if you have a response curve like this, okay, this is stress against strain, this is a plastic curve, okay. I could have nonlinear elastic behavior, that is, I load up and down along the same curve. Here I load up and come down along a different curve, okay. So, this is essentially a nonlinear elastic problem. This is plastic problem. Here there is dissipation. You could have also geometric nonlinearities, geometrically nonlinear problems, where the strain is the green strain, that is, it is a function of not only del u del x here, for example, but it will also have the other parts, which is half of del u del x whole squared plus half of del v del x whole squared plus half of del w del x whole squared. So, this is one. We may have various sources of nonlinearity. We could have lossy material. In any material which has loss in the or dissipates energy in its response, that will lead to a nonlinear phenomenon, okay, to a nonlinear problem. We are not going to look at these very complicated problems, but we will look at the essence of solving nonlinear problems through a very simple one-dimensional problem. We go back to our bar problem, okay. So, here is our bar subjected to an end load P and in actual load Fx, as we had been doing till now. We are not talking of the time dependent problem now, we are only sticking to the static problem, and this is resting on a elastic support, but so this is a continuous elastic support. Imagine that this is a rubber pad on which this is resting. So, elastic support, but here the elastic support can be modeled as a distributed spring with spring constant which changes with the position x, okay. So, we will have the spring constant in such a way that the elastic spring constant will be given through a constant part plus something which depends on the displacement itself, okay. So, let us say I have this quadratic effect. So, this is a nonlinear spring, nonlinear spring, okay. So, if you see that the K1, if the K1 is positive, then we have essentially, as the displacement increases, a hardening behavior. If the K1 is negative, as the displacement increases, we get a softening behavior, okay. So, accordingly we have this kind of a representation of the spring. Let us take the K1 to be positive. Now, the question is, how do we go ahead and bring it in our formulation? So, what will change with respect to our formulation? Again, we will take, if I come here, I will take a small piece at a distance x, okay, and in that piece I look at equilibrium. So I look at this piece at a distance x. Here is the force Fx delta x. Here is the axial force F at x plus delta x. Here is the axial force F at x. And since we have put it the spring on both sides, we will only get an axial force effect of the spring, which will be opposite to the motion, which is given as k0 plus k1 u squared into u delta x, okay, because this is given as spring constant is given per unit length. So that into the length delta x into the displacement of this part, okay. So if I look at the equilibrium equation, I will get F at x plus delta x minus F at x plus Fx delta x minus k0 plus k1 u squared u delta x. This quantity would become df dx delta x by expanding fx plus delta x about x in linear expansion, ignoring the higher order terms, and this is going to be equal to 0. Okay, so this is what we will have. So now we can cancel off or throw out this delta x parts, delta x, delta x. So what we get is df dx plus f minus k0 plus k1 u squared into u is equal to 0. Okay, this is our nonlinear problem. Now here f as a function of x is equal to, as we had done earlier, Ea du dx. So in terms of u, it becomes d dx of Ea du dx plus f of x minus k0 plus k1 u squared into u, this is equal to 0. So this is our differential equation corresponding to equilibrium. Okay, next what do we do? Next we would like to get to the weak formulation. How do we go to the weak formulation? We start with the weighted residual formulation. So weighted residual here, again we do the same thing as we have been doing till now. We take this expression, multiply it with a w and integrate from 0 to L. Put a dx here. We integrate it from 0 to L. Again we make the same arguments that here the second derivative of u is sitting. Okay, so we would like to relax the smoothness requirements on u, so we will do an integration by parts. Integration by parts will lead to integral from 0 to L Ea du dx dw dx plus k0 plus k1 u squared uw dx is equal to integral 0 to L fw dx plus P into W at L. This is our weak form. Okay. So this I am sure all of you can derive with your eyes closed, because this has become so standard in all the things that we have been doing till now. You have to start from this step in order to be able to construct a finite element approximation. So now we have the usual requirements, that is, what is the smoothness requirement on U and W? We want du dx, dw dx to be defined, so we can do with C0 elements, C0 approximation. Okay. So again we can construct a mesh of elements with nodes 1, 2, 3, 4. Let's say I've made 5 nodes, coordinates x1, x2, x3, x4, x5. Okay, and again we can make the basis functions. I'm taking the linear ones here. You can extend it to the higher order one using exactly what we have been doing till now. So this becomes my phi 1, this becomes my phi 2, this is my phi 3, phi 4, phi 5. So again my UFE as a function of x is equal to sigma I is equal to 1 to n. In this case n is equal to 5. Let's put as coefficients ai into phi I x. This is our representation of UFE. Okay. Now what do? We put this in the approximation, or in the form that we have obtained, the weak form, and we'll also put W is equal to, of the same type, sigma beta I phi I x. Okay. So now we said, since W is under our control, this is the representation of W. So we choose W equal to phi I x and put this along with the UFE in the weak form that we have obtained. So I will get here EA sigma AJ phi j prime into phi I prime plus I will get K0, okay, into sigma AJ phi j plus K1 into sigma AJ phi j whole cubed, whole thing multiplied by phi I, integrate the whole thing dx. This is equal to 0 to L f phi I dx plus p phi I at L. This is what I would get if I simply went and did a substitution. This is UFE prime, the derivative of UFE. This is UFE. This is UFE cubed. Okay. Now you see, the problem is that if I go to this ith equation, because remember, when I choose W equal to phi I, I will get the ith equation. This ith equation is no longer a linear in terms of this coefficients AJ. It is now, here it is linear, this part is linear, but here it will be a cubic in terms of the edges. So this is nonlinear in terms of the edges. Now what we had been doing till now, we were solving k into a is equal to f. Now because of this term being present there, I cannot write it in this form directly. Okay, so we have to do something. So what do? We essentially do linearizations. So what do? So we do a linearization. What is the basic idea here? Okay, so we will use an iterative solution technique in this, because it cannot be written in this form directly. You cannot get a solution vector A by simply inverting k, because now k will also be a function of the A itself. So we have to make a guess, start from the guess, go to the next solution, go to the next solution. So we have to solve iteratively. So iterative solution. Okay, idea is I start with a guess value of the vector A, just like we had done in the time integration, go to the next value A1, go to the next value A2, and so on to AI till convergence. Convergence means that the vectors, the new vectors that I get, we hope that the new vector that I get starting from the previous guess vector is an improvement over the previous vector. And finally, the vectors that we get do not change much in some measure. We have to give what is the measure that we are talking about. Okay, so we have various ways of doing this nonlinear solution. The two primary ways which are quite often used are, one is the direct iteration, and the other is what we know as the Newton-Raphson. Okay, so what we are going to discuss now in this lecture is the direct iteration method. Okay, so here in the direct iteration, what do? So we say that if I go back to my weak form, what we will do, we will write this quantity, this part in the direct iteration as k1. I know the solution at the previous step, I minus 1 Fe whole squared into UFE at I. Okay, here this will be UFE at I, this will be UFE at I. So what we are doing is we linearize it about the previous solution. That is, we assume that this part is known from the previous solution. Okay, this is an approximation. This will not be the exact solution. So what we do here is we are going to rewrite this weak form, integral from 0 to L EA, okay, sigma AJ for the step I, phi j prime whole thing into phi L prime for the ith step we are doing, okay, plus K0 sigma AJI phi j into phi L plus K1 into UFE I minus 1 whole squared into sigma aj for the ith step phi j into phi l. Okay. This is equal to 0 to L f phi L dx plus p phi L at x equal to L. Okay. So, this is the nth equation for the ith iteration. Okay. So, if I write it like this, really this quantity, if I look at this one, what would this be? This would be sigma a j from the step I minus 1 phi j that has to be evaluated. Okay. So, this is the nth equation for the ith iteration. So, now can I write the stiffness entries? So, stiffness entries will be, so I will have a k, I would put it as Lj for the ith iteration. Okay, this I wouldn't put it like this, k for the ith iteration into a for the ith iteration is equal to f as such. Okay. Now, what is happening here? This we have now obtained from this linearization, because if you see that these coefficients, now you see that this equation is linear in terms of the coefficients aj for the ith step. Okay. So, where now we will have k Lj for the ith iteration is equal to integral from 0 to L Ea phi j prime phi L prime, this remains unchanged, plus k naught phi j phi L, this also remains unchanged because this is the linear part, here there is no nonlinearity, plus I will have k1 into UFE from step I minus 1 whole squared into phi j phi L. This is dx. So, I can write this part of the integral as k linear Lj, and this part of the integral as k nonlinear Lj. Okay, this part. So, always my stiffness matrix will have the linear part and the nonlinear part. Now, the question is, how do I this part is very easy, we have already done it many times in our 1D analysis. How do I take care of the nonlinear part? Remember that now this will reduce to an element wise integration procedure, because we are going to now write everything in terms of the element equations. So, the global basis functions will reduce to element shape functions. So, let us say I have these shape functions. Okay. So, in the element, so let us say I was this 1, 2, 3, 4, 5. This is my element 2. Okay. So, this is now my global phi 2 and phi 3, and in the element level n1 of element 2, this is n2 of element 2. So, when I am doing this integration, I am going to construct these element matrices first, and by summing them together by using our assembly procedure exactly the same way as we had done for the linear problem, we will get the nonlinear equation. So for the element 2, let us say I want to now get the element matrices. Okay, so this is, if you remember, this is phi 2, n1 of 2, phi 3, or n2 of 2. This is node 2, node 3 globally. Locally it is node 1, node 2. So let me put the local one with a different color. Okay. So if I have to now construct the UFE I minus 1 in this element 2, it will be equal to, what will it be? It will be A2 coming from step I minus 1 phi 2 plus A3 coming from step I minus 1 phi 3. Okay. So this is how we can construct the finite element solution coming from the previous step for the current step. So this would be equal to A 1 I minus 1 for the element 2, n 1 of the element 2 plus A2 from the step I minus 1 for the element 2, n2 of 2, where A1 for the element 2 is this, A2 of the element 2 is this, n1 of 2 is this, and so on. Okay. So this is the representation of the finite element solution coming from the previous step. So I have to store these coefficients a1 to an for the previous step in order to be able to construct the solution in the element at the current step. Okay. Now this is one thing. Then in the calculation of the elements difference matrix, so I will have by the same token k for the element 2, okay, corresponding to the step I will be equal to, will have the components k, l, j for element 2 corresponding to I, step I. This will be equal to integral from x1 of element 2 to x2 of element 2, where x1 is the global x2, x2 is global x3 of EA n L of element 2 prime and j of element 2 prime plus k0 n L of element 2 into n j of element 2 plus k1 UFE I minus 1 in the element 2 whole squared into n L of element 2 and j of element 2. F calculation remains the same as in the linear case. Okay. So here this is a crucial difference from what we had done till now. This part we had already handled, okay, and okay, if I can do this, now how will I do the assembly? Again I will go to what does this L correspond to globally, what does this J correspond to globally, that row and that column I am going to assemble it in. So for example, L equal to 1 will correspond to the global 2, J equal to 3 will correspond to the J equal to 2 will correspond to the global 3. So everything remains the same. The only thing is that I have to carry this information from the previous step and use it here. Now this again we do using numerical integration. So what will we do? Let's say I have the element and here I have some gross points in the master element. So again we will go to the master element. These are psi m are your integration points, okay, in the element. So k Lj for the element 2 will become integral -1 to 1 by our standard mapping. The mapping remains the same, that is x is equal to x1 of element 2 n1, the linear n1 of element 2 plus x2 of element 2 n2 of element 2, which actually this will be written in terms of psi and eta, in terms of psi n1 hat, which is a function of psi, n2 hat, which is a function of psi. So everything, the rest of the procedure remains exactly the same. So I will have this one as EA n L derivative with respect to psi, n j derivative with respect to psi, okay, into 2 by L2, sorry, 2 by length of the element 2, which is the Jacobian, plus k0 nl hat nj hat length of the element 2 divided by 2, okay, plus k1, okay, UFE I minus 1 in restricted to element 2 whole squared n L hat n j hat L2 by 2 d psi. Okay, so everything else is exactly the same as we have done. Now what will we do? We will replace it by summation. So we will evaluate these quantities at the Gauss points, sum them up, multiply by the weight. This also has to be evaluated at the Gauss points. Now using the representation that we have here, UFE at the Gauss points, how will you evaluate at the Gauss point psi m? I have to obtain the value of the shape functions at these Gauss points, find, multiply with these coefficients, find the value of UFE at that Gauss point, put it in this expression. So it will be a number which I have to put in this expression. Okay, so if I do this, then I get the element matrices. Okay, so then what will I do? I will have k I AI is equal to F implies A for step I is equal to Ki inverse into F. Okay. Question is, how long do we continue? Okay, so once I have these coefficients, then I have to check. So to check, what do I do? So I find the vector Ri is equal to F minus Ki into Ai. What is this vector called? This vector actually gives me the error in the solution. So this is called the residue vector. Okay. So this is called the residue vector. So when I have this residue vector, then if the solution is the exact solution to the problem for the current step, okay, then I should get the residue 0, okay, which means that as the solution converges, the size of this vector, the residue vector, goes closer and closer to 0. Okay, so one way of checking for convergence is I will find the residue vector dotted with itself which is nothing but the length of the residue vector. Okay. If I take the length of the residue vector and I say that, well, if this length is less than equal to some tolerance which I set, okay, maybe it is 0.01 for example, I am happy. I could also use the normalized length, because if the displacement vector is small, okay, as for the given problem, then obviously I expect the residue vector to be also small. Okay. Now for that small thing, if I try to see this residue, I will get convergence very quickly, but in that small displacement vector my errors could be large. So I could use the scaled residue vector divided by the length of the vector AI, okay, is less than equal to the tolerance. Okay. So this is one more thing which is a better measure. It will be a more demanding measure which ensures that my error in the solution is under control. Okay. And I can set this tolerance to as small as I wish, depending on the accuracy that I desire from the solution. I could have other measures for the stopping criteria, but this is a good enough measure. Okay. So length of the vector AI would be square root of vector AI transpose AI. Okay. So with this we can check if I can get convergence or not. Okay. So what does this method really do? Okay. So this method actually achieves convergence in the following way. So let us say that this is my f, or the forcing function, and this is my deflection delta. Okay, maybe the tip deflection. So this in the nonlinear problem, let us say it goes like this, let us say. So what this method does, it starts with a tangent here. When you have the initial guess, it starts with a tangent at this point, at point x equal to 0. So let us say the size of the load is this. The load value that we want to go up to is this. So it goes up to this solution, gives me this. This is my delta 1. Once it does this, then it finds, well, there is this much gap between what I am getting and what I should get. Okay. So then now it takes this solution and creates this straight line, okay, passing from the origin to this solution. Okay. So difference of the current solution with the 0 solution. So it creates that, then it reaches this point. Once it reaches this point, then it sees, well, I have come down, this is my gap. Okay. So if I come down, this becomes delta 2. Once I get this delta 2, then I say, well, now let me start with this. So I create a line through this point. Okay. You see that I am coming closer and closer to the curve, and I hit this point, find this gap. Okay. This is my delta 3, and I continue this way till I reach this point, which is delta n. So in some iterations I reach this point. Okay. There is not, I mean, it's not true that always I will be able to converge, I may diverge also, but in general for such problems this will lead to convergence. Okay. One thing that we should note is that as I am coming closer and closer to the solution, exact solution of the corresponding to this load, the reduction in the error becomes slower and slower. So the convergence of this method falls off as we come closer and closer to the solution of the problem, and it ends up taking many iterations to converge to the solution. Okay. Many times in nonlinear problems, okay, you may have this kind of a situation. Okay, this is essentially a snap back situation. You may have this kind of a situation, snap through situation, where this method will fail. Okay. So now anyway, before going into the merits or demerits of this method, let us also go back to what we have done here as far as the solution is concerned, and remember that at every iteration I have to enforce the boundary conditions for the vector ai. So for example, in this problem we will always have a1i equal to 0. So we have to play the same game with the stiffness matrix that we have been playing till now in order to enforce a1i equal to 0 by taking care of the rows and columns corresponding to the first unknown displacement. Okay. So this, remember, we have to do at every iteration. Okay. So now let's come back to our discussion here. Okay. So this method has its problems, but nevertheless this is quite an effective method, and it can be used for a large class of nonlinear problems where the nonlinearity is not too far away from the linear solution. Now, what is my initial guess? A good initial guess in this problem, for example, in the problem that we have taken, where did it go? Okay, will be the solution of the linear spring. Okay, so it would be the case where I solve this problem with k1 equal to 0. So I solve the linear problem where, okay, then if I solve this linear problem, I will get, let me say, I will get k linear into a0 is equal to f. Okay. So this linear problem is what we solve. First, get the initial guess, start with this a0 and then proceed to a1, a2, a3, a4. Okay. Next, let's look at how to take care of this anomaly, how to improve the rate of convergence here. So let's go back and make the picture on a bigger scale here. Here is my level for f, and here is my actual solution, exact solution to the problem, and I start off first with this approximation, which is like the linear solution. I come to this. Okay, so I will get, this will be actually the way I have done, this will be my delta 0. Okay. Now, once I have this, instead of going with this line to the next solution, what if we took this line, which is the local tangent at this point? Okay. If I took the local tangent, you see that I have improved so much. The gap has come down. Okay. So instead of taking this line, I took the local tangent at this point, and I went along the local tangent and I got this solution. So if this is my delta 1, you see that I am very quickly very close to the exact solution of the problem. This kind of approach where I use local tangents to the curve This is called the Newton-Raphson method. Okay. So what we are going to do in the next lecture is we are going to take the Newton-Raphson method and describe how do we use it in the finite element setting for this generic problem that we have taken, and exactly the same procedures have to be used when I am doing any other nonlinear problem. Okay. So I'll stop.